So let's do the Fourier transform of a square function using this graphical approach. Now this square function is going to have both even and odd terms, so it's going to have a cos omega t and a sin omega t part to it. So let's get started. We start off building up the Fourier transform. So if we know this function here, e to the minus I omega t, well, that can be split into two. It's going to have a cos omega t part and a minus I sin omega t part. So that's going to be shown in graph 1 or figure 1 and figure 2. We then modulate that surface, that is, we multiply it by the function f of t, and again we multiply that by the function f of t for the sine section as well. So that's going to be shown in figures 3 and 4. We then integrate from minus infinity to infinity of that function f of t times cos omega t by dt, and the minus integral from minus infinity to infinity of f of t I sin omega t by dt, and those are going to be shown in graph 5 and 6. And finally, whenever we add both of those together, we're going to get our Fourier transform, which is the f of I omega, which is equals the integral from minus infinity to infinity over f of t e to the minus I omega t by dt. And this is going to be shown in figure 7. In figure 7 we're going to show it in terms of a graph, which is a three-dimensional graph, which will have the real valued and the complex valued part of the function as a function of time. And also I'll split it down to just the real value and just the complex value. And finally, in the very last page, we'll go through the entire example on one layout. But first of all, we need a function f of t in order to find the Fourier transform. So let's go ahead and we'll pick a function. So here's the function here, and it's a simple square function. It's got height 1, the length there is 4, that's a function of time, and it just says f of t, that's a function of time. So nothing new in this. Notice that this function is neither completely even nor completely odd. It has both even and odd terms. So we start off with the cos omega t surface. So here's our time along this axis and omega along this axis. So that's graph number 1. You'll note here that the time is slightly different. The previous ones I showed the time was along this axis and the frequency along that axis, but it doesn't really matter. So here's the minus I sin omega t surface. Again, we've seen that previously. There's our time and there's our value for omega. Now we have the cos omega t surface, which has been modulated, that is multiplied by our function f of t. So you can see here that we have our function f of t, which is a height 1 and a length 4, and that has multiplied that cos omega t surface. So we're only left with this one section of that cos omega t surface. Now we do the same for the sin omega t surface, and we'll see we've got our f of t and it's multiplying that minus I sin omega t surface, and you can see that we have this square function here of height minus 1 and the distance along is 4, and it's modulating this surface here, which is our I sin omega t. Now we integrate this function f of t, which is modulated the cos omega t surface, from minus infinity to infinity with respect to time. So we're integrating in this direction here, which is our time axis, and when we integrate in this direction, which in effect is adding up all the values along this direction across this line, then we will get this function here, which will be a purely real function, and it will be the sinc function which we've seen before. We then integrate from minus infinity to infinity of the function f of t, which has modulated the minus I sin omega t surface, and you can see that here in this drawing, and we're integrating in this direction. When we integrate in this direction, we get this other function here. And this function is a purely imaginary function. So this axis here is an imaginary axis. So finally, we're left with the Fourier transform. So this is the original function here, which is height 1, and it's got the length 4. And this is the Fourier transform of the function. Now you can see it's in 3 dimensions. Now I'll show you in Matlab just in a minute, and you'll be able to, it makes it a bit easier to work out how we can get the real and imaginary parts. But this is a 3-dimensional function, so we've got frequency here, got the imaginary part and the real part. So the Fourier transform is a function of the frequency, and it has an imaginary and a real part to it. So this is the real part of it, and the real part, as I've seen, is a sinc function, and it's a purely real, and it's an even function. And here is the imaginary part, and you can see it's a purely imaginary function, and this function is odd. So we'll go ahead and we'll look at these functions in Matlab. So this is the function in Matlab, and as you can see, it's a 3-dimensional function. So we have the independent variable, which is the frequency, and then we have the dependent variables, which are the imaginary part and the real part here. So I can turn these round, and as you see, as I turn this corkscrew type shape round to the real axis, you'll see that this gradually heads up towards that function there, which is a purely real function, and we've seen that in the previous slide. Now I can also move it to the purely imaginary axis, and that's it shifted to the imaginary axis there. Okay, so it allows you to see how you can generate the real and imaginary parts from that 3-dimensional function. So we'll go ahead now, we'll look at the entire Fourier transform, and we'll see it done in Matlab. So this is the entire Fourier transform of that function, split up as we have shown on the previous slides. Now it's a little bit small here, but you will have access to this here in the resources section. So if you've got access to Matlab, you can open it up and have a little play with it yourself. So we have our original function f of t here, and I've taken that original function, take a copy of it over here as well. That original function modulates this cos omega t surface, so you should be able to move that surface round about. Okay, and it modulates the minus sine omega t surface here, and you've got the functions here which have been modulated. So that's the sine omega t times the f of t, so that's the modulated surface, and then there's the f of t multiplying the minus sine omega t surface, so that's the other modulated surface. And then when you form the integral, you get the real part from this cos omega t f of t, and you get the imaginary part from the sine omega t f of t. Now finally, whenever we look at the Fourier transform, as we've seen in the previous diagram, the Fourier transform is shown in a 3D manner. So we've got the frequency along one axis, then we've got the imaginary and real part up the other axis, and you can move these round about in order to get the real and imaginary parts. So in general, you wouldn't see the Fourier transform drawn out in a 3-dimensional manner like this. You'd always see it with either the real part and the imaginary part drawn separately, or more commonly we would have a magnitude and a phase plot. So this here is the magnitude of the plot which has been generated from this function here. So if you like, if you were to take an axis along the centre here, the magnitude would be the distance from the axis to a point on the curve. So we'd just simply be using the Pythagoras to get that, so it would be the imaginary squared plus the real squared, and the square root would give you the magnitude. And you can see from here what you get is a raised sinc function. And also the phase is generated and shown in a phase separate phase plot. So that shows you a complete derivation of the Fourier transform of a square wave. And I've got it printed out here as well, so I suggest if you've got access to Matlab that you can take that out and you can work through the derivation yourself, and you can convince yourself that you understand every single facet, every single part of the Fourier transform of that little square wave. So thank you for listening. I'll get you in the next video. Goodbye.